Session. Okay. It's from my interview, so maybe, but you have 30 minutes plus for discussion.
Okay. So thank you very much for inviting me to give a talk here. So we're going to change gear a little bit to look at the numerical side of how to simulate turbulence in a tokamak. So this is a work that we've done in NTU together with the CEA team. For people who may have heard this code called GZL, gyrokinetics semi-Lagrange code, and has been in CA for like 20 years, mainly developed by Virginie and the team. And we took over the electromagnetic part of it last year, and then we started to work on it to make it a feasible tool to simulate plasma turbulence in tokamaks. So a little bit of background. I'm not sure how many talks have talked about this, but I guess there must be a lot last week and this week. We touch base on what is actually happening in a tokamak. So here is a cross section of a tokamak, okay? And the color here is the electrostatic potential. So sometimes you have a negative, sometimes you have positive. But let's say if you zoom in here, take a small patch and just zoom in, you will see contours of electrostatic potential. And if you calculate the E cross B drift, right, the E would be perpendicular to this contour. And then B is in the direction going into the paper or coming out of paper. And then you see that E cross B drift will be going in the iso contour line. So basically, if you have a particle and then you let it go in with the E cross B drift, you complete this kind of orbits, right? Okay, so what is important is that this is a way that energy and density get mixed between the inside of tokamak and the outside of tokamak. Suppose you are having a fusion plasma, which is very hot in the center and relatively cold at the edge. And this kind of walking will somehow mix the very hot and the very cold, right? In general, the temperature will be lower. And this is not very good because what we are looking for is the fusion triple product, which has temperature. Also, it's a problem of confinement time because if you move energy from inside to outside very quickly, and you're lowering the confinement time. So overall, this is a reduction to the performance of the fusion device. So that's why we are very interested in studying turbulence in plasma in tokamaks. Now, what is new in this picture? Because this picture has been discussed many years, is that in future fusion device, in ITER or in the I would say demo or the actual thing that's working, you will get a lot of helium as a product of the reaction between deuterium and tritium, and these helium are very high energy. So the burst energy is at 3.5 MeV. As they go around the plasma, they collide with the background, and they will somehow slow down. But basically speaking, in the end, you will get a soup of plasma, which is the background, and on top of that, you got a population of fast particles, what we call fast particles. The energy of the fast particles are in the range of MeV, a few hundred keVs, but basically they stand out because their energy is high. So the story is that these fast particles will interact with the turbulence and in many different ways. One of the ways that people have been looking at in recent years is the interaction between some waves that they have excited, and how does that wave interact with the turbulence background. So this particular wave is called alpha negative mode. Alpha negative mode is kind of a fluid agar mode. You can think about the plasma somehow as a rigid chamber, right? You have a rigid chamber, and you have normal modes that is oscillating, right? And these particles, it happens that the orbit frequency of these particles is matching the frequency of these normal modes. These normal modes will exchange energy. there will be exchange energy between those modes and the particles. And those modes will be excited, and they will interact with the turbulence background. There are many ways they could interact, but people have been discussing mostly this recent years that there will be zonal flows that are driven by the alpha negative modes. And those zonal flows, as you will know, that they will tear apart the turbulence eddies. And then this is a way to suppress the turbulence. So that's why we are interested in this problem. So one of the experiments recently published in 2022 shows that actually if you have really got a very high energy particles, in this case would be a jet experiment with some kind of heating scheme called free ion heating scheme. It's a way to generate NEV phasons because in the tokamaks these days, there's no, actually it's not very much fusion reaction happening, so it's not too much helium inside, high energy helium. So you have to mimic the scenario using some other means. So in this way, they have heated this, actually I think it's deuterium into very high energy NEVs using this this way of, I think it's ICH. And then it actually excites the alpha negative mode. And then what happened is that by comparing a shot without this alpha negative mode and with a shot with this alpha negative mode, people have shown that the temperature has increased when you have the alpha negative mode when compared to when you do not have it. And also the diffusivity is way lower in this case. So this on the bottom left figure is a plot of the frequency versus time. So it's a spectrogram of the oscillations, of the magnetic oscillations. And these very strong lines are the signature of that alpha negative mode has been excited. And this also corresponds to when the temperature actually increases. So this is strong evidence that the phasons will perhaps stabilize the turbulence. And this is very good for the future reactors, of course. This is not just a single case. In the some recent experiment, this has been reproduced. In one of these recent DT2 jet experiments, the same thing happens. And more recently in D3D, Xiao Xu has also shown that something would happen similarly. The mechanism, although people have been discussing about the zonal flow suppression scenario, but it's still up to debate. Now, what we are going to do, we are trying to do, is to use this very brilliant code, Gisela, and try to see if the same thing can be reproduced, or we want to study the mechanism of such a suppression. So Gisela is what we call global flux-driven sweat gyrokinetic flow. So global means that it takes the whole domain into simulation, not just a strip of it. Flux-driven means it's not simulating the fluctuation around a fixed background, but rather it evolves the background at the same time. So basically, evolve the whole distribution. Actually, it's driven by a source in the center. So that's a flux-driven sweat. It uses the semi-Lagrangian scheme, where I'll talk about later. It has multiple ion species, which is exactly what we need because we need fast particles in the picture. There were three kinds of electron models. The one that we're going to use is the fully kinetic model. So why do we need fully kinetic model? Because we need to have currents, right? So currents is the alpha negative mode somehow has you need the current to be in the picture to be able to excite them. So if you want a current, then you need the kinetic electrons to give you the current. In this case, we have a relatively simple boundary condition, which make a buffer region around the tokamak. So somehow the perturbations will be damped in the buffer region. The shaping is not taken into account, so we're looking at some kind of circular cross section. So boring, but the first step. Well, historically, the hold has been electrostatic. Preliminary electromagnetic version has been developed by the PhD work of Camille Pilot. And then we took over last year, and then we started to build on top of it. And then we are happy to say that we have a version that is almost ready for practical use. So what Gisela can do, global gyrokinetic simulations of the whole tokamak with phasons, everything is very expensive and problematic. because the simulation is usually very costly. So you're looking at something around the 10 to 20 to 30 mega million CPU hours per simulation. So it's very, very costly. And it also has to resolve multiple space-time scale interactions. So if you're not careful, you'll be computing something that's not meaningful. Also, whenever we have the magnetic perturbation, often the code becomes very prone to instabilities and noise. And this is just because in the problem, we have added a fast time scale, which is the alpha wave, and the electron motion, which is very, very fast. So we have to be careful because this makes the equation that we're solving much more stiff. Also, I have to say that there are many already published results by the Gene team, by the OC5 team, and the GTC team. So we are kind of new in this business. But we have also our benefit is because Gisela is intrinsically full F and global, and has been recently discussed the need for a global code to be able to solve this problem by the senior, because traditionally people have been trying to use some local code, which takes a flux tube and simulates the turbulence along the flux tube, and top of that add fast science. But it has been shown recently that this is not sufficient. So Gisela is in a very good position because we are intrinsically full F and global. Now I have to go into a little bit of the equation side to see to tell you what we are solving exactly. First, we start with the gyrokinetics. Hopefully, we have touched on. I mean, some other speakers may have touched bases on what gyrokinetic is, but I view it as a change variable. So we are trying to move from a coordinate that describe each individual particles to something like a gyrocenter coordinate, such that we have somehow averaged out the fast motion of the cyclotron motion. And in the gyrocenter coordinate, the mu, which is the so-called magnetic moment, is an adiabatic variable. So very good, because we have reduced 1 degree of freedom in our equations, coming from 60 to 5. So this is on the right-hand side is a kind of plot that I took from Xavier's paper to show you what's the difference between the particle, which is this red dot going around, and then the guiding center, which is the blue dot, which is the center of the orbit, and also the gyrocenter. So the gyrocenter and the guiding center are not exactly the same. They're displaced. There's a displacement due to polarization. But basically, you can view it as somehow a way to transform the coordinate into the somehow a guiding center or the gyrocenter. Now, we usually start with Lagrangian. So the Lagrangian has been given by Little John. We take it here. So equilibriumly, so say if you set up some kind of electric magnetic field in the background, and then you write it in such a form, you take the variation of that, and then you'll be able to get how the equation of motion for the particles in the coordinates of your choice. In this case, the coordinate that we are choosing here are the x, right? The x is the location of the gyrocenter. U parallel, which is the velocity of the parallel velocity, how the particle moves in the parallel direction, and mu, which is the magnetic moment. So now, after we write this, we can use the variational principle to get equation motion. So which I'll skip. I just tell you that this is the way that how we construct equation motion. And now let's suppose that we have perturbation, right? On top of the Lagrangian that we had before, now we have added perturbations. So the one on the top here is the equilibrium one, so the one without perturbations. Now we have added perturbation, which means that the perturbation we contain a part that is A tilde, which is the fluctuation of the magnetic vector potential, and that of the phi, which is the electrostatic potential. So it goes one will go into the Hamiltonian, that's this one, and whether we treat how do we treat this A tilde is up to there are two ways to do that. So I don't know why why we have this huge thing here. So I'm just going to remove before we proceed. You cannot see what is behind, right? Right. Let me delete.
The French way. Must be a winner.
Yeah, yes, exactly. Oh, I cannot even modify this time. Activate. Oh, okay, activate modification. Right. Let me just get rid of this thing first. Hopefully not, yeah. Okay, so there are two ways that we can proceed. The first way is that since we have added a perturbation of the A, which is the vector potential, we can put it alongside with the parallel velocity, and we define a new variable called the canonical momentum. So which now have the parallel velocity, and on top of that, perturbation part, and use that as the new dynamical variable, and then we can proceed with the variational principle. Well, this has a huge benefit in the sense that if you look at the equation of motion for the parallel velocity or the parallel momentum, there's no time derivative as you would do if you compare it the other way around. So this is one way that you can do it. The other way is that we don't do this. We just keep u parallel as variable. We keep the parallel velocity as variable, and then we do the same business. Well, if you look at the velocity equation for the p parallel, then you see that there's a part to do with the partial time derivative of a parallel. So why so? Because, well, actually the time derivative of a parallel is the parallel electric field, right? So if you have a parallel electric field, it will add on the parallel velocity, and that's the natural way that this will proceed. The way that we do on the left-hand side is that if you put together the two into a new variable, you somehow this parallel electric field is contained already in your parallel momentum. So you do not have this new you do not have the time derivative here. So why are we saying that this way is the winner for this case? Because numerically speaking, if we have a time derivative here, and then this will also appear in the velocity equation, and the velocity equation will go into the how do we evolve the distribution? A distribution will go into the M-Pace equation and the Poisson equation, and makes the numerical scheme very difficult to implement, because then we have to look at the an implicit scheme. So traditionally, people have been favoring the left-hand side, which is what we call Hamiltonian formalism. By the way, the name here, Hamiltonian formalism and symplectic formalism, are just the jargons or the historical way that we call the two different approach of implementing this. So traditionally, people have been using the Hamiltonian formalism. However, this will lead to another problem, which is what we call cancellation problem. So let's suppose that now we know that the equation of motion, just by taking the variation of the Lagrangian, okay, suppose this can be done. And then, the velocity equation would just be f dt equals 0f, being the distribution function in the variable of x, x nu, and p parallel. And then you can write a chain rule to expand it in terms of characteristic. So this can be done, right? However, we also need the two equations for the field to close the problem. So the Poisson equation would just be the quasi-neutrality in this case. If you don't look at this term, so suppose you don't have this first term, then you would be just the quasi-neutrality. You have the density, the charge density being 0, which includes the guiding center part and also the polarization density. So this is pretty standard. The Ampere equation would be just taking the parallel direction of the curl B equal to mu j. But bear in mind that because we have expressed our quantities in p parallel, not u parallel, so we have used canonical momentum and we haven't used the parallel velocity. So when we compute the parallel current, we have to take the moments of the distribution function, right? But here we can only take the moments of p parallel, not u parallel. But however, we know that in p parallel, there's already a part that is to do with the a parallel, which is contained inside. So in order to balance this, we have to add another term on the left-hand side, here on the left-hand side, which we call skin current, to balance that, such that what we are actually computing on the right-hand side is the moment of u parallel, not p parallel. Okay, so that's why we have this actual skin term on the left-hand side. Now the problem is this is also numerically challenging, because if we're looking at the size of those two terms, we realize that this skin current term is very, very big, very, very big compared to the other terms. And because on the right-hand side, we are also in the p parallel, we have this term as well. Right? We have this term as well. These two terms needs to cancel. So left-hand side and right-hand side containing the scheme current, we need to cancel. However, if we are not doing this carefully, numerical noise will dominate this process because you are trying to make sense of a very small number out of very too big number. So you're trying to get the 1.01, the 0.01 out of the 1.01. So therefore, the noise and signal noise ratio is not very good. If you look at the formalism, well, of the symplectic way, you figure out there's no such a term. So in this case, if we were talking about the cancellation problem, the symplectic formalism is similar. So how do we get? How do we make take the advantage of the both formalism? Well, in 2017, Mischenko has put forward a mixed variable scheme, which he's saying, let's suppose that the A parallel can be break into two parts. One of them is the symplectic part, the other one is Hamiltonian part. Right? The split is actually quite arbitrary. So you can choose whatever the symplectic part is, and then the rest will be the Hamiltonian. So he chooses it in such a way that the symplectic part is very big. It's almost dominating the Hamiltonian part. The Hamiltonian part is relatively small. And therefore, when we're looking at a cancellation problem, if we're trying to cancel the two terms, and when the Hamiltonian part is very small, then there's no cancellation problem. So this is the way that we take to code it up in Gisela. The other problem is how do we do with the parallel time derivative, the parallel time derivative A parallel. So this one can be solved by taking a proxy for that. In this case, Mischenko has decided that let's take the proxy of ideal with D. So let's just fix in such a way that the parallel, the time derivative of A parallel symplectic part just be the parallel gradient of phi. So if we're looking at this equation of the time derivative here, you can just basically replace that by B dot grad phi. And therefore, the time derivative of A parallel does not explicitly appear in the advection equation. So problem is solved. There are a lot of other subtleties in this process numerically, but I'm just presenting you the basic, the way that this can be done. Now, okay, so now we are back to the real business of Gisela after we have talked about this for 20 minutes. I've only got, I think, 10 minutes, so let's be fast. So Gisela uses this thing called the semi-Lagrangian scheme. There are actually three schemes that people have been using so far. The one way is to do particle simulation and collect the charge density and the current at the grid point. This is called the particle in cell method. On the right-hand side, there's this grid-based method. So you basically do everything on grids, right? Just a finite differencing, a finite element. So what Gisela uses is this thing called a semi-Lagrangian. So basically, you still have a grid, but what you do when you're solving df dt equals to some collision operator. Suppose that you don't have a collision operator, you'll be just solving df dt equals to 0, right? Which will mean that if you start from one point here, you trace the trajectory, the distribution function will be constant along this trajectory. So what you can do is that you at the next time step, you just backtrace this trajectory, and then you may land somewhere in the previous time step. And this previous time step is not on the grid. So basically it's somewhere in the middle of the grid. And then you can do an interpolation because you know all the values of the distribution function on the grid points. And this scheme is called the semi-Lagrangian scheme. So the core algorithm of Gisela is to iterate between solving the field and the velocity equation. So basically, you start with some guess of the field, right, at some time step, and then you can use them to advect your particles, or you can use them to solve your distribution function using the semi-Lagrangian scheme. And then you will get in the distribution function a new time step, right? And then you use this to compute the current density and the charge density, and then you put this back to the Maxwell equation, and you will know the field in the next time step. So basically, you do the iterations like this. Okay, now it's time to show a little bit of result that we achieved. The first, we've done a number of benchmarks to make sure the code is working. the first thing that we did is to compute the alpha wave frequency in a larger spatial tokamak with a flat profile. So basically, you think about the tokamak as just like a street cylinders, very large aspect ratio. In that case, there's a simple relationship between the frequency of the alpha wave and the alpha velocity, and the ratio is just this k parallel, which is the parallel wave number. So the parallel wave number can be related to the toroidal mole number and the toroidal mole number by n divided by q minus n divided by r naught. So basically, you know all these, and you can form an analytical equation for what is the frequency as a function of q, which is the safety factor, and that of the beta, which is the how do I say, the ratio between the dynamical pressure and that of the magnetic pressure. So you can do a benchmark. So you can plot the frequency of the theory versus what you get from Gisela. And here we're showing that it's matching in the case of both a fixed beta by changing q and a fixed q by changing beta. So by the way, thanks Michael, which is my PhD student, who helped me to complete this test. And another test that we normally do to make sure that the code is working is to look at the transition between the ITG, which is short for ion temperature gradient mode, and the KBM, kinetic ballooning mode. So these are two different instabilities that happens at different beta. The base case that we are always using is so-called cyclone base case. It's kind of like a tokamak with a circular cross-section, and you can specify what are the profiles of the pressure and temperature. So here is the on the right-hand side, you see this red one is the temperature, and N is the density. They both have a highest gradient and mid radius. So on the right-hand side, this is the gradient depicted the gradient. So normally you expect instability to be excited at where the gradient is the highest. Okay. On the left-hand side, it shows the Q profile mass. It's just a pretty standard tokamak Q profile. So this is the result that we are comparing to the gene code, which they published in 2016. On the left figure here is scanning beta. So this is the beta of the plasma. Okay, and on the y-axis, this is gamma, which is the growth rate of the mode. So as you start from 0 beta, you expect to excite ITG. As you increase beta, the growth rate of ITG will decrease, and at some point, a new branch of instability, which is called the kinetic ballooning mode, will take over, and the growth rate will increase. So you basically see these structures typically in the growth rate. On the right-hand side, we're also comparing the frequency of the ITG and the KBM versus gene. So both cases we show very good match. This on the right here is some kind of a phi, which is the electrostatic potential in the 2D cross-section. So this is a very typical ballooning structure and also aligned with the result of other codes. Now, finally, we move to a case. We do ITG simulation non-linearly, flux-driven with collision. So we look at a case where we call economy CBC. Economy CBC is the same as CBC as I showed before, except that we have reduced the parameter to make the calculation less challenging. The two parameters that we have reduced is one of this is the ratio between the mass ratio between the ions and electrons. This used to be 1,800-ish, but now we reduced to 100. This is not realistic at all, but it's a way to reduce the cost. The other parameter that we have chosen is rho star, which is the ratio between the lumbar radius and the minor radius. So we reduce it to 1 or 100 instead of normally speaking for tokamak 200. The beta we have chosen is 0.5%, circular geometry. The grid size here is pretty small for Gisela, because Gisela used to run with 512 or 1024. But this is relatively small just for testing. And the time step here is pretty small as well. And this has some subtlety to do with the CFL condition of the algorithm. But basically, we're taking a relatively small time step, just to let you know. So we have added histors and collisions. Oh, yeah, yes, yeah. To be able to finish. And the diffusive buffer at the boundary. So the cost of this simulation is around 1 million CPR. On the right-hand side, we're showing the plot of phi for different ends versus time. So you see that growth and saturate as a point at some point. And this one is the electric static potential of the n equals to 0 mole, so the donor mole. So it starts with some kind of a new classical value. And then when the turbulence is excited, it starts to oscillate because of the generation of zonal flow. Okay, so this is also showing the 2D slots, 2D cross section of phi. So we start from a ballooning structure linearly, and then start to see the zonal flow get generated and start to break the turbulence eddy. And finally, we end up into a steady state where we see turbulence eddies in the whole domain. Okay. This is the how the temperature and density evolves. Well, the point of this plot is to show that we start with this blue curve. It's not very obvious, but we start with the blue curve at t equals 0 initially. And then finally, we have a relatively saturated or steady state in the end, which is a balance between the source, that is pumping the whole thing, energy source pumping the whole thing, and the turbulence transport. So we reach some kind of nonlinear steady state, which is flux driven, has the source, has the collisions, and also electromagnetic effect. So this is something that something new. Finally, we can calculate the particle balance. This is a way to show that the code is working properly or not. Basically, you take the continuity equation and then you compare the time derivative of density versus the flux term, and they should be exactly the same. So this is for ions and this is for electrons. We see that for ions, it's quite good, except that at radius of 0.7, there's some kind of a mismatch. And if you roll back here, you see, if you look at a 2D plot, there's some kind of alien thing that's happening at the outer radius, and this is usually the indication of the grid resolution not enough. So if to make a better match in the particle conservation, we need to increase the grid resolution for that. Anyway, as a summary, we presented a theory and numerical algorithm of the Gisela, the electromagnetic version, which is almost ready for, I would say, physics studies. And we showed a good match for linear benchmark, including TAEs, which I think Shrish will show next week. And nonlinear test is ongoing, and we are showing promising results. I think that's it. Thank you.